So in a first semester introductory calculus course, the first topic you usually see would be limits, and after that, you usually cover continuity. Well, what exactly is continuity? Well, in layman's terms, the answer is that it's the ability to draw a function without having to lift your pencil off the paper. And when speaking about continuity at a point, a function is continuous at points where you're able to get from one particular point on the function to ones with immediately adjacent, should be adjacent x values without having to lift your pencil off the paper. So let's say we're looking at this function here. Let's call it function 1. It's defined over the open interval c to d. So that's excluding points c and d. And you can see that given any point on this function, you can get to the points with immediately adjacent x values without having to lift your pencil off the paper. And that holds for any particular point on this function. So we can say it's continuous at all points in its domain. Now let's say we're considering this function here. Let's call it function 2. And it's also defined over the open interval c to d. And you can see here that you can get from every point on the function to ones with neighboring x values. So say from here to the ones immediately with x values immediately adjacent to it without having to lift your pencil off the paper. And yes, this function has some sharp edges, but that does not affect your ability to draw it without having to lift your pencil off the paper. So again, this function is also continuous at all points within its domain. These sharp edges have to do with a different idea called differentiability, which will be covered at a later time. Now that we've talked about where a function is continuous, where's a function discontinuous? The answer is that the function is discontinuous at points where you cannot get from one point on the function to those with immediately adjacent x values, or where the function is not defined. So there are several ways in which a function can be discontinuous, and we'll refer to these as the types of discontinuities. Now we're going to go over several examples of each of the types of discontinuities. So now we're looking at a function. We'll call it function 3a that's defined in the open interval c to d. And it looks like, let's say we start here, we can get to immediately adjacent or function values with immediately adjacent x values without having to lift our pencil off the paper. I should say points on the function with immediately adjacent x values without having to lift our pencil off the paper. But when we get to point A, we have a hole where this function is not defined, so we have to lift our pencil off the paper till we get to the right side of point A, after which we can get to the adjacent values without having to lift our pencil off the paper. This is a specific type of discontinuity, or this is an example of a specific type of discontinuity called a removable discontinuity. So what's a removable discontinuity? So a discontinuity on the function lowercase f of x is classified as removable when there exists a continuous function capital F of x, we'll just call it capital F of x, that's identical to lowercase f of x except at the point of discontinuity. So that's quite the mouthful, right? So we're saying that this function here has a removable discontinuity, and we know that this point of discontinuity is at a, right? At x equal to a. So we know that this point of discontinuity is removable when there's a function that's identical to this function except at x equals a, and that function is continuous. So the function is identical to this function except that the function is a continuous function that's identical to this function except at the point of discontinuity. And here we know that there exists such a function, because what would happen if we fill in this hole? If we filled in this hole, well, we'd have a continuous function. We have a function now where we can get from every point on the function to points with immediately adjacent x values without having to lift our point off the paper. This was the problematic point, but this new function, capital f of x is actually, it's continuous at this point A as well, because you can get from point A to the points around it without having to lift your pencil off the paper. Anyway, here's the original function with the hole in it, and this hole is called a removable discontinuity. But this hole where you're undefined at this value A is not the only type of removable discontinuity. Here we have a function that's very similar to this function. However, at x equals A, instead of being undefined, is defined kind of above where you'd expect it to be defined. And to get from points left of A to, or points with x values left immediately less than A to the point f of A, you have to kind of jump above and jump back down to get back on the function, so you do have to lift your pencil. But this discontinuity is also removable because because there exists a function here that's the same as this function except at this point of discontinuity. And what's that function? Well, it's the function which at A, instead of being defined here, is actually defined where this hole is. So this is another way you can have a removable discontinuity. Here you are undefined at point A, so you can remove this continuity by filling in the hole. Here you're defined at point A, but you kind of have to jump up to point A. And here this function can be redefined and made continuous by moving this point down to where the hole is. And another term you may see in place of removable discontinuities is the term point discontinuity. So both of these functions, both of these points of discontinuity here, in addition to being referred to as removable discontinuities, are also called point discontinuities. So you may see that term as well. Now there are other types of discontinuities besides removable discontinuities. Here we have a function, we'll call it function 4. It looks like you're able to draw it without lifting your pencil off the paper until you get to this point. Let's call that point A, where the function takes a leap up, way up to here, after which point you can continue drawing it without lifting your pencil off the paper. But this type of discontinuity here, because it involves a jump, it's named a jump discontinuity. I'm going to abbreviate DISC. You'll sometimes also hear the term finite jump discontinuity. So we said this type of discontinuity is an example of a discontinuity that's not a removable discontinuity. So why is that? Well, if you remember, a removable discontinuity is one for which there exists a function, another function, identical to the original function, except at the point of discontinuity, which is in this case point A, but that function is a continuous function. Is there any function that's continuous that's identical to this function except at this point of discontinuity? Well, let's see. So let's say if instead of a hole here, if the hole were here and were filled in at this point, so let's say we had a hole here instead filled in here, would that make this continuous? No, because you'd still have to jump from here to here to draw the function. There would be no way to draw this function without lifting your pencil off the paper. In fact, if we had a hole both at the bottom end, the top end, and the function were defined, say somewhere in the middle, you'd still have to lift your pencil off the paper. So there is really no way to make this discontinuity a removable discontinuity. There is no way to make this, to redefine this function with a function that's equivalent except at point A, and that function being continuous. No such function exists. Now let's contrast this with example 3b. In contrast to example 4, 3b here, you can actually redefine this function by, instead of having the point here, value of the function at x equal a, here you have it where the hole is, and now you can draw the function. So instead of this here, you have this. Now you can draw the function without having to lift your pencil off the paper when you get to x equals a. And I think the real reason here is because you're tending towards the same value as x approaches a. So kind of clued you into the fact that continuity does have something to do with limits. Whereas here in example 4, coming in from either side of a, you're really tending towards opposite values, so there is really no way you can redefine this function at x equals a that'll enable you to draw it without having to lift your pencil off the paper. So if there's a finite jump discontinuity, you'd probably be thinking there's some sort of infinite discontinuity as well, and there certainly is. So that's this example here. In this case, you can draw the function without lifting your pencil off the paper until you get to x equals a, at which point there's a vertical asymptote. So to the left of x equals a, the function creeps up towards positive infinity, and immediately to the right of it, it creeps up from negative infinity. And this function is once again defined on the open interval c to d, and it's not necessarily the same c and d used in the other examples. It's just an arbitrary c and an arbitrary d. Hopefully you can tell that there is really no way to redefine this function at x equals a in order to be able to draw it without lifting your pencil off the paper. You can put the function at value at a anywhere, and you'd still have to lift your pencil off the paper to get from, say, positive infinity out to negative infinity. So this is called an infinite discontinuity. So infinite DISC, and it is a non-removable discontinuity. This jump discontinuity that we just looked at was also non-removable. But going up to positive infinity on one side of the point of discontinuity and coming up from negative infinity on the other side of the point of discontinuity is not the only type of infinite discontinuity you will see. In fact, on either side, you could be going up to positive infinity on both sides, or I should say going up on left side, coming down from positive infinity on the right side, or you could be going down to positive infinity on the left side and coming up, going down to negative infinity on the left side and coming up from negative infinity on the right side. These are also considered infinite discontinuities. So these are both also infinite discontinuities. And these are non-removable discontinuities as well. So there really is no function that's identical to each of these functions except at the point A that is actually continuous. And to understand that, you have to realize that, let's say you defined this function at negative or positive 10 billion at x equals a. Well, there is, as you get even closer to a, you'll get to points even bigger than positive 10 billion, because remember, this approaches positive infinity as x approaches a. So let's say you're at 10 billion here, right at a. Well, just to the left of a, you could be at 10 trillion. And the same is the case just to the right of a. So really, there is no way to draw this function, to redefine the function at x equals a and be able to draw it without lifting your pencil off the paper. And the same idea applies in this case when you have the function heading towards negative infinity to the left of a and heading up from negative infinity on the right of a. At a, you could be defined at negative 10 billion, and to the left of a, as you approach a from the left, you certainly could have negative values that are much more negative than negative 10 billion. And and the same is the case on the right of x equals a. So in this video we covered what it means for a function to be, what it means graphically for a function to be continuous at a point. In the next video we're going to actually cover what it means graphically for an entire function to be termed continuous. Rather than just at a particular point, what does it mean for a function to be a continuous function?